We're going to finish section 2.7. We had talked about implicit differentiation, just a little bit of a background of where we were headed. Our goal is that there are times when it's either not convenient or not possible to solve an equation for y. And when that happens, we need to be able to take a derivative still with the x and the y potentially on the same side of the equation. When we do that, it's called implicit differentiation. And we talked through four examples last time of how to do that. And we're on example 5. So example 5 wants us to find locations of horizontal and vertical tangents. So thinking with me for a moment, anytime you see the word tangents, what is it telling you about tangent lines? What is the direction saying you have to do? You're going to find the derivative. Okay, so the phrase tangent lines actually tells you something about finding a derivative. And then we're finding where they're horizontal and vertical, which means different pieces of things are going to happen to be 0. So if you've got a horizontal tangent line that's like this, what's going to be equal to 0 when you have a horizontal tangent line? Do you know?
Horizontal tangent line.
The slope, which is called the derivative, right? The slope would be 0 on a horizontal tangent line. So when we have a horizontal tangent line, we're finding where the derivative equals 0. What in the world about this vertical tangent line business? I mean, we did not have that in our last sections of material. Do you know what happens to get vertical tangent lines? You could have something like an asymptote going on. So when I was sort of drawing in the air my horizontal tangent line, some of you said the slope's 0. What can you tell me about the slope if it's vertical? It's undefined. So what we're wanting is an undefined slope. And how do we get an undefined slope? You probably have a 0 in the denominator. So this vertical tangent line business, we're wanting to have a slope or a tangent. We'll say tangent since I did that a moment ago. We want the tangent to be undefined. And that's going to mean for us that we're going to have a denominator that's going to be equal to 0 as we're working with the problem. Okay, so half the battle sometimes is in understanding what the directions are wanting you to do. Because if you just start doing something and that's not what they're asking you to do, then you're sort of up a creek. So we're going to be finding a derivative first. So let's see what you can remember about implicit differentiation. It's been a couple days, right? All right, x squared. What's the derivative of x squared? 2x. That's just like normal. What about the y squared, though?
2y, dy, dx.
Right, 2y, and then we have to do dy dx. Because y is a function of x, or at least it's an equation in terms of the variable x. What about the derivative of negative 3y?
3 dy dx or just 3?
Yeah, it'll be negative 3, and then we're still going to have, you're right, dy dx. Because the derivative of y is dy dx. And then this equals what? 0. So last time what we did here at this point is we sort of continued to keep the pieces that had the dy dx together, and we moved everything that didn't have dy dx to the other side. Do you guys remember that? So that's, in this case, that's only the 2x. That's the only thing that's going to move. And I'll put this negative 2x on the right. On the left-hand side now, the two pieces that are underlined in red both have dy dx in them. So what can I do with the dy dx? Factor it out. It's almost like you guys did homework on this. But I know you didn't. We didn't, right? No. Had other homework to do. All right, so we have dy dx times 2y minus 3 equals negative 2x. Now what? By what?
2y minus 3.
Right. We're going to divide by 2y minus 3. So my slope, dy dx, equals negative 2x over 2y minus 3. Okay, everybody good with where we are so far? Okay. So let's do the horizontal tangent first because it was listed first. That's the one that we've done most frequently as well. So let's talk about horizontal tangents. So if the horizontal tangent, that will be where the derivative equals 0. So I want the dy dx, which is negative 2x over y minus 3 to equal 0. How is this going to equal 0? Yeah, if the numerator in particular, right, Noah? If the numerator equals 0, and for this numerator that is x is equal to 0. But there's a catch, because when it talks about a location up here, what do you think it's referring to?
Ordered pair.
An ordered pair, and this is just the x value of the ordered pair, right? So if I know that my x equals 0, how can I figure out what y equals?
Plug in 0 for that x in your equation.
Yeah, the original equation, right, Will? Yes. So I'm going to use my original equation, and I'm going to plug in my x equals 0. So in essence, I have 0 squared plus y squared minus 3y equals 4. Well, that gives me a quadratic, y squared minus 3y equals 4. How do I solve a quadratic equation? Factoring. Yeah, we're going to reverse FOIL. We're going to factor. And in order to factor, it means I need to get that 4 to the other side. All right, so you can't just factor out the y from these things and solve. You have to have everything on the same side set equal to 0. So this is y squared minus 3y minus 4 equals 0. And we'll factor. How will this factor?
Minus 4y plus 1.
Right, minus 4 and plus 1. That gives me the negative 3 in the middle, and it gives me the negative 4 at the end. So what are my two y values? 4 and negative 1. So I'm going to sort of write those as ordered pairs with the fact that x equals 0 here. So I have 2 points, 0, 4, and 0, negative 1. And these are answering the question about horizontal, right, tangent lines. These are points of horizontal tangency. Okay, everybody good so far? Yes.
So, just tracking what you did again,
Mhm.
you're seeing where the derivative equals 0.
Right.
So, negative 2x equals solve for x.
Mm-hmm. And it isn't necessarily solve for x, it's the numerator, right? Which ends up being a solve for x on this one, right? Okay, go ahead.
Then you plug in the 0 for your x.
Mm-hmm.
How much do you solve down for again? And in the original equation, you get the point.
Yes.
Is it possible to have an x in the denominator?
It could. We could have an x in the denominator depending on the function we were dealing with, absolutely. There's nothing special about the fact that this actually ends up being x on top and y on bottom. It just did on this particular one. Let's solve the other one now. So the other piece that we're supposed to be finding is the vertical tangent locations, right? Like the vertical tangent lines. Gotta have more space. All right, so for our vertical tangent, we need to have the denominator of the slope equal to 0. So my dy dx was negative 2x over y, 2y minus 3. Is that right? So I'm wanting my denominator, 2y minus 3, to equal 0. Okay? So 2y is equal to 3. Y is equal to what? 3 halves?
Equal to 3 halves.
Good. So y is equal to 3 halves. So again, that's only one part of an ordered pair. So how do I find the x coordinate that goes with it?
Put it back in the
Original equation. It's just not quite as clean as the last one, although we don't have to factor, which is kind of nice. So I have x squared plus 3 halves squared minus 3 times 3 halves equals 4. Okay, help me out. What is 3 halves squared? Yep, 9 fourths. What is 3 times 3 halves? Negative 9 halves. And this is equal to 4. I'm going to have to combine all of the constants at some point, right? So I might as well go ahead and write them as a common denominator. So 9 over 2 can be written how? Yep, 18 over 4. And how can 4 be written? 16 over 4. All right, so on the left-hand side, 9 over 4 minus 18 over 4 gives me, yep, negative 9 over 4. And I'll add that to the other side, right? So what is 16 over 4 plus 9 over 4?
25 over 4.
25 over 4. How nice. Because what's going to happen next? Square root. What's the square root of 25 over 4? Is it just 5 halves? Uh-huh. Yeah, a plus or a minus. Which means in writing the ordered pairs, how many ordered pairs am I going to have? 2. One of them will be 5 halves, 3 halves, and then the other one will be negative 5 halves, 3 halves. So these are the places where I have vertical tangent lines. There's quite a few steps, but the algebra is actually pretty clean on this particular one. Did you have a question?
So you have to leave it to plus or minus 5.
Yes, because we put the square root into the problem. If we'd actually had a negative and then squared it, it would have also given us a positive 25 over 4. So that's why the negative will still work. So there's 2 locations where I have vertical tangent lines. There's 2 locations where I have horizontal tangent lines. Now, this graph, the reason this is happening is, do you know what the shape of this graph actually is? Your calculator won't let you graph it, but do you know what it is?
Is it a semicircle?
It's actually a circle. Yeah, it is actually a circle. The coefficients have, well, we have x squared and we have y squared, and the coefficients in front of both of them are the same. If they were different, we'd have something called an ellipse, which looks kind of like an oval. But this is actually a circle. So think about the picture of a circle. Can you visualize why it's going to have 2 horizontal tangent lines? Can you visualize why it's going to have 2 vertical tangent lines? Yeah. So this makes sense that there's 2 locations for each of those particular points. Yes, Luke?
What kind of circle though would it be with an extra variable? So these
It-
are missing circles, so I can square them y squared.
You've seen them in ordered pair form. This is just going to be a circle that's not centered at the origin. That negative 3y, if we were to complete the square, it's going to be shifted. Yeah, the x, it will be on the x-axis because x doesn't have a minus anything next to it. But because it says y minus 3, this is actually going to be shifted, let's see, to the right. And the center would actually be at 3 over 2, be at 3 halves. So that's what would be happening there. Do you have a question, Chance? Yeah.
Yes. Could you go back to the page with the vertical tangent line?
Yep.
Get the last part.
No problem. Yeah, so that's what's going on, Luke, is that it's just a circle that's shifted to the right, basically off of the origin, shifted to the right. And it will have a radius. It won't be a radius of 2 because that 4 on the other side will actually manipulate as well when we change, if we were to change it into standard form.
So like what would, like, so we can all, like you can see why they would have 4
Yeah.
tangent lines. Could you kind of show what that would look like?
Mm-hmm.
Just
So it would look something like, hang on. Okay, my scale's not going to be quite right, but it looks something like this. I don't know that it hits the origin either. It may not. We'll draw it like this. So here's the center. So if I were doing horizontal tangent lines, they're going to be up here at the top and down here at the bottom.
oh, okay.
And if I were doing vertical tangent lines, they're going to be on the sides, which I'm not going to be able to draw very well. But we'll do with red, like on the
I
sides.
didn't know how they would be because could they pretty much be anywhere on it almost?
No, because it's horizontal.
horizontal,
Yeah.
yeah.
So it'll have plenty of tangent lines, just there will only be 2 that'll be horizontal.
I see it now.
Yeah. Okay. Let's take another example. This one says find the second derivative. And again, I talked about how your book likes to use the double prime notation. And this is fine, but you can also use the notation. And this is one that I'll be using just for consistency from what we've been doing before. Let me get it in the right place. That's what it looks like. It's, sorry, and then I use that big red fat pen. All right, this is the derivative, the second derivative of y with respect to x twice. That's the notation for it. So we're going to find a second derivative, right? That's the goal. As we do this, we're going to find a first derivative first, and then I'll show you how we deal with this because it's a little bit different since it's implicit than the last time that we found a second derivative. All right, so what's the derivative of x to the 2/3?
2/3 x negative 1/3.
Excellent.
I'll study.
How about the derivative of y to the 2/3?
2/3
to the negative 1/3, then what? dy dx first. Yeah, and then it's equal to 0, you're right. You don't have to worry about any dy dx's on your quiz today, right?
Hallelujah.
No dy dx's, yeah. All right, the goal is then to solve this for dy dx. So we'll move the piece that's not dy dx over to the other side. So I have 2/3 y to the negative 1/3 dy dx equals negative 2/3 x to the negative 1/3. I think multiplying by 3/2 would be a really good next step. What do you think? This is x to the negative 1/3, right?
Negative x.
Oh, yes, thank you. It is negative. And then you can either think about multiplying or dividing. I'm just going to divide, and we'll write it that way. We're going to divide by y to the negative 1/3. So dy dx will equal negative of this. And if you don't like the negative exponents, if you don't find those especially friendly, you can switch them, and you could write this as y to the 1/3 over x to the 1/3. Remember, that's a property of exponents. Or you could even write this as negative y over x to the 1/3. And I'm going to use this version of it to do my next step because I find it to be the cleanest. It's not the only one. You could use the step before that red box if you want to do it. So there's a version, or a couple of versions anyway, of dy dx. And we do want the positive exponents at the very end of all of this anyway, because we started out with positive exponents. All right, any questions so far? So if we were just asked to find the derivative, we'd be done, right? But we're being asked to find the second derivative. So we're going to take this equation, which is dy dx equals negative y over x to the 1/3, and we're going to take a derivative. So this is the second derivative of y with respect to x twice.
Oh, was the negative?
Yeah, I've got
That
it.
was-
Or if you want to write that as y double prime, that's fine, especially now because it's not going to get mixed up with anything else at the moment anyway. Okay, on the other side of the equation, though, we got a little bit of a mess because, well, I'll show you why in a minute here, but let's do the chain rule, right? Because I've got something raised to a power of 1/3. So what do I do with the 1/3?
Come on down.
Okay, it's going to come on down, like on The Price is Right, right?
Yep.
Okay, we have y over x. What's going to be the new exponent?
Negative 2/3.
Negative 2/3. And the next part is going to be the derivative of y over x. Well, the derivative of y over x, that's a quotient rule, exactly. So what am I going to have?
X times dy dx minus y all over x squared.
Right. All right, so here's the deal. When I do the derivative of the y over x, I write the numerator, that's x. I do the derivative of I write the denominator, that's x. And then I do the derivative of the numerator, which is dy dx. And then I have minus y over or minus the opposite of those derivatives over the denominator squared, which is x squared. The reason this is messy is because do you see the dy dx in the middle of what's going on? That's not especially friendly. And the deal is, actually, since I've got that dy dx in there, I know what dy dx equals, don't I? It equals negative y over x times to the 1/3, which means I'm going to do a replacement as I'm doing all of this, and I'm going to take this, and it will substitute in for the dy dx, because they're equal to one another. Which is going to look a little messy for a little while, isn't it? Yeah, it is. So let's take a look. All right, so we've got the negative 1/3 here. We've got the y over x to the negative 2/3. And then we've got x times negative. In fact, can I just put the negative in front of the x? Are you guys good with that? Okay, and then I've got the y over x to the 1/3 minus y all over x squared. And the worst part of the whole process is that we're going to have to clean that up. Okay, I know. That's part of it. We will. So let's actually talk about cleaning up the x times the y over x to the 1/3 business. So I'm going to write each of these with the exponents applied to the variables now. This is y to the negative 2/3 over x to the negative 2/3. Over here, I have negative x times y to the 1/3 over x to the 1/3 minus my y all over x squared. So what's going to happen right here? The x and the x to the 1/3.
They will cancel.
To what?
2/3 x to the top.
Yeah, so this becomes x to the 2/3. It's just subtraction. This has an exponent of 1. So we have 1 minus the exponent of the 1/3 on bottom, so that's actually 2/3. So this is x to the 2/3, y to the 1/3 minus y over my x squared. And I've still got that negative 1/3 in front. We'll deal with him at the very end. Oh, there's a negative there. I didn't say. I just didn't get it written in yet.
Oh, I'm sorry.
You're fine. I didn't have it there. I'll put a dot there just for good measure. All right, so yes, now we're going to multiply straight across the top, multiply straight across the bottom. The denominator is the easy part because there's no addition or subtraction. So I'm going to associate the negative here with the 1/3 with the 1 on top. So this is going to be negative 1 on top, all right, so that I have a place to decide where to put that. The denominator is going to be 3. What is x to the negative 2/3 times x to the 2?
X to the 4/3.
Yep. All right, so we're adding. All right, so we're adding negative 2/3 plus 2, and if you get a common denominator, that would be 6/3. So negative 2/3 and positive 6/3 would be positive 4/3. All right, across the top, do you see all those negatives? I have negative 1 at the beginning, and then I have a negative x to the 2/3, and then I've got a negative y, right? So I'm going to get all positives on top, right? When I multiply that first negative at the beginning times each of the negatives further on, I'm going to get positives. So my signs are going to turn into positive. And then I don't really have to deal with multiplying by 1 because it doesn't change anything. But I've got the y to the negative 2/3 that I'm supposed to be multiplying or distributing, we could say, through each of these, right? We're going to distribute. So if I take the y to the negative 2/3 and I distribute it to this piece, then the x to the 2/3 doesn't change. But I've got y to the negative 2/3 times y to the 1/3, which is going to become what? Y to the negative 1/3. And then I'm going to have y to the negative 2/3 times y, which is going to become what? Y to the 1/3.
Can you switch the y to the negative 2/3 and x to the negative 2/3?
You could.
Do that. Would that be easier?
It just depends on how you see it. I'm about to do something else different here in a minute, and that'll change it too. But yes, you could definitely do that. Right now, the problem that I think Noah is seeing is that we still have a y with a negative exponent in a problem, right? And our answer is incomplete as long as we've got that negative exponent here. So if we've done it from this perspective forward, which I actually think I did something completely different in my book, in my stuff here, but when I was writing my notes, what I would suggest now is we need to get that y to the negative 1/3 into the denominator, or at least get it out of the numerator. And we can't just throw it down into the denominator because there's addition on top. Are you guys with me? So that's not helpful. Yes?
So you distributed, is that right, with the y?
Yes, I did.
Negative 2/3. So whenever you distributed the y to the negative 2/3 times the negative x to the 2/3, what happened to the y?
Well, I
Oh, there it
distributed
is, there it is.
yeah, I distributed it to the whole piece that's in blue, that's circled there in blue, because it's multiplication, which means I combined the pieces that are alike. Yeah, so basically we're multiplying y to the negative 2/3. Ignore the negative x, the negative part of the x. X to the negative 2, or to the positive 2/3, and y to the 1/3. So that's what's all being multiplied together, and then I can multiply it in any order. Well, I chose to multiply or combine the two pieces that have y together because they match. I have a way to combine those.
So do we just split the fraction?
On our y's, it's just like, whenever I look at the y going to the x, I feel like it would be x, y.
Okay. It is, that's why you've still got the y here. It is x, and there is a y piece. What's going on here, Chance, is it's like when you learned back way a long time ago, is that if you multiply 5 times 3 times 2, you don't actually multiply 5 times 3 and 5 times 2, right? You multiply it by one of them because one of them is already multiplied by the other. You can do the multiplication in any order. It's the same thing that's happening here, but with variables. So we're changing the order of the multiplication to combine the pieces that are alike. All right, so here's the deal. We've got to get that y to the negative 1/3 to go away. My suggestion is for us to multiply by y to the 1/3 on top and bottom. Yes, Luke?
Can't you just factor out the y to the negative 1/3, make the other y to the 2/3, and then just bring it down?
It's the same thing. That would do the exact same thing that I'm doing here. Yeah. So if I multiply or if I factor out a y to the negative 1/3 and then move it, I'm going to end up getting the y to the negative 1/3 in the first box multiplied by the y to the positive 1/3. And what happens when I have a negative 1/3 and a positive 1/3 exponents on y? My question is this. If I have y to the negative 1/3 times y to the positive 1/3, what happens? Yeah, the exponent's 0, right? Not the whole thing, but the exponent. So y to the 0 power. What is y to the 0 power? 1. Okay. It's the equivalent of factoring it out in front. I'm distributing it through. And in doing so then, like you guys said, I get x to the 2/3 times 1. And then I have y to the 1/3 times y to the 1/3, which is y to the 2/3. And then my denominator, I have 3x to the 4/3, y to the 1/3. This is your final answer for dy dx. d2y dx2, or y double prime. And there's no simplifying you can do in the end because the pieces of the denominator, the 3, the x, and the y, do not occur in both of the terms above them. They only occur in one or the other. The cleanup for that's the worst. Agreed?
Yeah.
Yeah, definitely.